Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University School of Engineering and Technology, SOET. Diploma in Smart City Development and Management, DSCDM. MIO 005 Smart Cities, Safe Water, Sanitation and Sustainability, Block-1 Water Supply in Smart Cities, Unit-3 Smart Monitoring of Water Supply in Smart Cities. 3.1 Water Monitoring and Auditing. Objectives. After studying this unit, you should able to explain water quality monitoring and auditing systems, describe SCADA in water management, gain knowledge in smart water meter and billing system. 3.1.1 Water monitoring. Water quality monitoring can be defined as the sampling and investigation of water quality parameters. These may include introduced contaminants into any particular stream, such as metallic compounds, pesticides, oil, etc., the contaminants originated from nature in water that can nonetheless be affected by human sources, such as dissolved oxygen into any stream, nutrients, etc. The scale of their effects can be influenced by the various parameters such as pH and temperature of the stream in which these contaminants are introduced. For example, the change in temperature shows great changes in the amount of dissolved oxygen present in the water, and pH shows an effect on the toxicity of ammonia. Most of the professionals of state, local and volunteers have been monitoring the water quality parameters from past many years. However, the preliminary way to identify the problems in meeting the water quality standards was done by using monitoring methods in past decade. At present, all the professionals, i.e., the water quality specialists, have started their approaches towards finding out a best monitoring methodology which can monitor all the physical, chemical and biological water quality parameters of the water. Water quality monitoring can be used for various purposes to identify whether waters are meeting desired water quality standards. All authorized bodies have recognized specific standards, limits on pollutants, classifying what concentrations of chemical contaminants are acceptable in their waters. When these contaminants surpass maximum or minimum permissible concentrations, waters may be incapable of supporting the beneficial uses such as drinking, swimming and fishing for which they have been selected. State water quality professionals evaluate water quality by associating the concentrations of chemical contaminants found in reverse streams to the criteria in the state's standards, and so review whether reverse streams are meeting their desired uses. The determination of existence of the aquatic life into a particular stream using water quality monitoring, however, might prove to be inadequate. Among several parameters affecting the aquatic life, the dissolved oxygen into the stream and the temperature of the water plays an important role in maintaining a healthy population of various aquatic animals. Moreover, the physical conditions of the stream will also play an important role in maintaining the same. In order to determine the suitability of aquatic life inside the waters, the biological monitoring methods generally proves to be better among the three methods, i.e., physical, chemical and biological monitoring methods. To identify specific contaminants and sources of contaminants, water quality monitoring helps link sources of pollution to a stream quality problem because it identifies specific problem pollutants. Since certain activities tend to generate certain pollutants, e.g., bacteria and nutrients are more likely to come from an animal feedlot than an automotive repair shop, a tentative link might be made that would warrant further investigation or monitoring. To determine trends, chemical constituents that are properly monitored, i.e., consistent time of day and on a regular basis, using consistent methods, can be analyzed for trends over time. To screen for impairment, finding excessive levels of one or more chemical constituents can serve as an early warning screen of potential pollution problems. Water quality program designing. The initial step in designing is to determine the purpose for which program is needed. The purpose determined will help in selection of the parameters to be monitored in the programming. The decision-making should be done based on following factors: determine different types of water quality problems along with the contaminant source from which it is generated. Overall cost available for installation of the monitoring equipment. To know about the accuracy of the equipment, know about the capabilities of the water quality specialists. It is very difficult to monitor toxic substances using different monitoring programs. Moreover, the overall cost required for these monitoring methodologies is also very high. However, the collected samples can be tested for heavy metals or organic pollutants present in it by sending the samples to various accredited laboratories. The most commonly used parameters that are monitored for a specific stream are stream flow rate of the stream, total alkalinity, biochemical oxygen demand and dissolved oxygen, pH, total solids, turbidity, temperature, phosphorus, nitrates, conductivity, and fecal bacteria. General preparation and sampling considerations. The section below describes the sampling technique used and equipment that are considered for evaluating most common water quality parameters. However, there are two tasks that are undertaken when sampling is done, which are discussed below. Task 1: Preparing sample containers. The sample containers should always be rinsed and cleaned thoroughly after usage so that the contaminants left over on the walls of the containers will not further interfere with the next sample. However, method to be adopted depends upon the parameter to be analyzed. Method A: General preparation of sampling containers. The following method should be used when preparing all sample containers and glassware for monitoring conductivity, total solids, turbidity, pH, and total alkalinity. Wear latex gloves. Wash each sample bottle or piece of glassware with a brush and phosphate-free detergent. Rinse 3 times with cold tap water. Rinse 3 times with distilled or deionized water. Method B: Acid wash procedure for preparing sampling containers. This method should be used when preparing all sample containers and glassware for monitoring nitrates and phosphorus. Wear latex gloves. Wash each sample bottle or piece of glassware with a brush and phosphate-free detergent. Rinse 3 times with cold tap water. Rinse with 10% hydrochloric acid. Rinse 3 times with deionized water. Task 2: Collecting samples. Generally, always collect the sample away from the banks of the stream in the main current and never collect the sample from stagnant water. The outdoor curve of the stream is often a good place to sample, since the main current tends to clinch the bank of the stream. In shallow sections, carefully push your way into the center of the current to collect the sample. For collecting the sample from deep sides, a boat is required. Mostly try to maneuver the boat into the center of the deep sides. 3.1.2 Water auditing. A water audit can be defined as the quantity of water wasted from water supply network and the overall cost of the wasted utility. It will measure non-revenue water, NRW, and unaccounted for water, UFW. The water audit always balance the quantity of water that is produced against the quantity of water that is billed. Complete audits gives the details that consists of the water system utility profile and water consumers records, which permits easy management of the water resources and also enhances the. It is a significant step towards water preservation and, if associated with a leak exposure plan, then it can also save the utility a substantial amount of man time. The water audit consists of the regular exercise carried out in order to evaluate the amount of water distributed through water distribution networks along with amount of water that is lost from the network while transport from the water storage facilities to the consumer's end. The water audit chart is prepared to make an audit report. Water balance chart is necessary due to following reasons. It functions as an outline for evaluating a utility's water loss conditions, calculating the water balance. A. It reveals the availability of the data. B. Increases the awareness about the water problems. C. Gives route for further developments. It is used as a tool for communicating and setting benchmarks. It provides noteworthy guidance obligatory for purposes of ranking consideration and investments of limited water resources. Components of water audit. Proposing rehabilitation program. Storage reservoir raw water gravity main. Raw water sump and pump house head works investigation of flow measurement against water balance sheet. Hydraulic modeling and analysis for existing distribution system. 3.2 SCADA in water management system is used for supervising, controlling and data acquirement. This system is capable of monitoring and controlling the whole water system, or even some parts of it. Moreover, it is also capable of generating outputs that are important for operation and maintenance of the system, creating graphs, reports, etc. Most commonly in water supply systems, these systems can monitor and control all the processes and equipments that are utilized, i.e. from distribution networks, inclusive of all transmission pipes, water treatment plants and all unit processes taking part in the system. However, in the urban areas these systems can also be used for storm water management and wastewater treatment plants. Benefits. The evaluation of the benefits that is obtained by installing the SCADA system in water company is based upon the improvements that will be provided by this system in terms of precision in analyzing various water quality parameters without laboratory requirement. Moreover, the proper functioning of all the unit processes operations in the water company is also taken care by SCADA system. Some of the important benefits that are generated due to installation of SCADA system are: I render higher efficiencies for all unit processes operation in water system. SCADA system can easily detect and prevent the failures that occurs in the water supply system. Provides a good service in comparison with the conventional methodologies used, specifically in terms of water quality, water flow rate and pressure of the water flow. Possibility of optimization of the chemicals used in various processes also can be reduced in certain cases as per requirements. The information extracted from SCADA system also improves the operation and maintenance facility, mainly the storage capacity of the system can also be improved in addition with the optimization of the operation of the pumping station and management of pressure. A SCADA system also results in reducing the overall energy consumption and cost required for the operation and maintenance of various units used in the water system. The SCADA system provides the information that generates a reduction in water production. SCADA provides a greater efficiency in controlling the leakage that may lead to various repair works resulting in a great water loss from the facility in very short duration. If the company endorses infrastructure asset management, IAM, the appropriate substitution of pipes and service networks also allows the decrease of the total number of non-planned repair works to render higher efficiency in maintenance. The second benefit is associated with the activities that takes place in water supply systems under maintenance department. SCADA systems reduce the overall costs of maintenance required in the water supply system. The information generated by the SCADA system helps in detection of the flaws that may take place during measurement of flow by flow meters. This will help in establishing better maintenance requirements, which will result in decrease in data failures due to very fast response. Due to the available minute information about the conveyance pipes performance, pumps power, water levels allows receiving information about the failures, which also reduces the severity, implies very less maintenance overall costs. 3. Reduction in overall water losses. The statistics delivered by SCADA systems enables the decrease of real losses in water supply systems. This technology permits an effectiveness increase in the leakage control due to fundamentally two reasons: tanks water levels monitoring, which permits the recognition of leakage and overflows, and night flow monitoring coupled with step testing, enabling easier sight of leaks. Subsequently, any small leak that goes hidden proves to be a possible future large-scale burst. This action guarantees, indirectly, a decrease of the quantity of water lost. In addition, the remote information about pressure and tanks water levels enables, directly or indirectly, an increase in the efficiency of pressure management, reducing real losses in water companies that perform pressure management. A faster response to non-planned repairs also contributes to reduce water losses. By monitoring the water distribution networks, the SCADA systems allow a faster detection and location of this type of failures, reducing its duration. If the water company performs infrastructure asset management (IAM), it is possible to reduce the number of non-planned repairs in pipes and service connections through its timely rehabilitation substitution. This is probably one of the most important measures to prevent real losses, and SCADA systems can give an indirect contribute by providing useful information. Finally, it should also be pointed that the reduction of real losses obtained through SCADA systems also results in the decrease of water abstraction charges, EU Water Framework Directive. 4. Improvement of sales and CRM. The improvements of effectiveness and efficiency previously mentioned, together with a faster response to non-planned repairs, result in a greater customer satisfaction, which, in turn, leads to the reduction of the number of complaints, particularly regarding service disruptions, water quality and the service levels. Deferment, downsizing or elimination of CAPEX-IN infrastructures. SCADA systems provide reliable information extremely useful to build simulation models of the water supply systems, and these enable the optimization of the expansion and rehabilitation needs, thus reducing a capital expenditure, CAPEX. The attainment of a good infrastructure implies a continuous effort in assets rehabilitation, replacement, renewal and reinforcement. 6. Improvement of the system's reliability and resilience. In extreme situations, for example in case of natural hazards, by remotely controlling and monitoring in real time the system operation, the SCADA systems enable a better decision-making, providing to the water company the ability to perform faster and better responses. In addition to the main benefits mentioned above, there are others equally important, such as the fulfillment of targets imposed by the regulation authorities. SCADA systems enable better operation and maintenance of the water supply systems, a reduction of water losses and a better management of the rehabilitation substitution needs, resulting in the improvement of the performance indicators used to evaluate the service provided by the water companies. 3.3 Water Smart Metering. BILLING. The water smart metering is used for collection of data from the meters of the customers, those who use water, gas or electricity. The conventional meter reading necessitates a person from the particular department to visit regularly to the location of the meter and record its reading. The reading that are noted down helps to assess the amount of water that has been used by customers, and accordingly the bill is generated monthly yearly basis. It is very difficult to note down the reading in person very frequently since the number of meters installed in particular areas are large in numbers. Therefore, smart metering is an option that can reduce the labor work and give accurate reading without any manual errors. Smart metering is also capable of detecting the meters that are not in good condition by communicating through alarms. The water company can use this information regarding the working conditions of the meter in order to enhance its services given to the customers. Benefits. The procedure used for quantifying and studying the benefits resultant of the installation of a smart meter (SM) system in a particular water company is alike to that already existing for the SCADA systems in water company. It started by evaluating the actions of the administrative processes from the value chain, classifying the tasks in which SM would generate value. The removal or drop of those tasks can also be expressed by equations with parameters modified according to any water company. Among all the benefits below are some important benefits mentioned. Reduction of costs associated to meter reading. Manual metering is very difficult activity which is to be done by different worker registering the readings by going in person at various houses present in the locality. However, there is always a probability of manual error that can take place. Smart metering is one of the solutions that can reduce a lot of labor work and record the readings very precisely, giving a direct benefit to the water company as well as the customers. Due to the manual error in recording the readings, frequent complaints against the water company employees are raised, due to which the company has to again send the another set of employees to note down the readings in order to cross-check and satisfy the customers. Most of the times the meters are situated at very remote locations, due to which the access for noting down the readings seems to be very difficult. Another source of benefit is the elimination of readings confirmation due to human error. If the water company has a proper accessibility for registering the readings, then the problem of rescheduling the visit of the employees from the company for noting the readings is avoided. The smart metering allows the real-time collection of data regarding the consumption of water for billing purposes, eliminating a probability of any errors. A reduction in the number of work accidents can also be expected once the employees committed to meter readings are no longer exposed to potential risk situations. 2. Improvement of sales and CRM. SAM has a significant impact on the reduction of CRM costs, customer billing claims due to inaccurate meter readings, and readings confirmation. By performing frequent remote readings, SAM enables early detection of customers' excessive consumption, leaks, preventing future complaints. Likewise, by always billing real-time consumption, complaints due to estimates above the real consumption disappear, thus reducing rebilling needs. As the water company can remotely access the meter's readings, if the meter remains at the consumption location, making new contracts or ending existing ones can be performed remotely and much faster, and this can be viewed as a new opportunity to improve CRM. The access to better and more detailed information enables the customer service to provide easier help to the customers. It becomes possible, for example, to make an instantaneous reading of the customer's meter as he is contacting the water company. 3. Reduction of water losses. SAM can also contribute significantly to reduce water losses. In the case of apparent losses, this technology proves advantageous in three main aspects: customer metering inaccuracies, unauthorized consumption, and data handling errors. Concerning the errors due to submetering, caused by the meter swearing, SAM can play an important role, warning the water company if the meter's maximum flow was exceeded. This can damage the meter or make it lose its accuracy, increasing submetering. In case of jammed, no-metering, or stiff meters, submetering, the SAM system sends an alarm informing that the equipment is no longer registering consumption or is registering values abnormally inferior to those of the customer's consumption history. Experience suggests that nearly 80% of the causes of measurement errors lie in nearly 20% of the meters. In this context, SAM appears as an important technology for the identification of troublesome meters, 80/20th rule. Sometimes customers with large meters have consumption patterns that do not fit the meter's flow rate range. In these cases, the detailed information provided by SME is crucial to identify the situation and enable an adequate sizing of a new meter. The data from SAM can also contribute to the detection of unauthorized consumption, another cause of apparent losses. With the detailed information about water consumption, together with the information from the SCADA system, the water company will be able to detect unauthorized uses of water. Another type of illegal practice is customers tampering the meters. In these situations, the SAM system immediately generates an alarm warning the water company, and this can significantly reduce the volume of water consumed between the moment in which the tampering occurs, when the meter starts measuring deficiently, and the moment in which normality is restored. Still, in the perspective of apparent losses reduction, crossing information about consumption from different utilities, water, gas and electricity, can eventually lead to an easier detection of irregularities. Regarding real losses, SAM can play an important role in increasing the efficiency of ALC. The water consumption monitoring allows the identification of abnormal consumption, which might otherwise be confused with the occurrence of bursts, generating false alarms. In the context of pressure management, By contributing to the water demand management, SM may prove relevant by allowing the reduction to even lower pressure levels, attaining greater reduction of the water losses. Data provided by SM allows the elaboration of more reliable and frequent water balances, contributing to a better definition of management and control methods. The reduction of real losses, besides the direct benefit from the water no longer lost, also leads to a reduction of water abstraction charges, EU Water Framework Directive. 4. Improvement of water network operation and maintenance, and meter management. SM system contributes to improve the operation and maintenance of the water network and the management of the water meters. These systems provide reliable consumption information especially useful for building network simulation models and for meter design purposes. Detailed information about water consumption also enables a greater efficiency in defining meter replacement needs, reducing the number of meters to replace before the legal term is reached. From the whole meters population, only a small fraction, usually corresponding to jam meters, accounts for a very significant part of the apparent losses. The percentage of stiff meters can also be significant and similar to the previous one. V. Deferment, downsizing or elimination of capex in infrastructures. For water companies that practice IAM, SM can produce considerable benefits. Due to the deferment, downsizing or elimination of capex in infrastructures. By enabling water demand management through the reduction of water losses, particularly real losses, and by informing the customers of the occurrence of residential losses, the water companies will be able to defer, downsize or even eliminate capex in infrastructures. Likewise, if the water company gives direct feedback of the customer's water consumption, then he will be able to reduce his consumption, and this also contributes to defer, downsize or even eliminate capex in infrastructures. SM increases the flexibility in tariffs, enabling the water companies to encourage customers to change their habits of consumption, especially in peak hours, seasonal periods or during droughts, mitigating peak demands and reducing the stress over the water distribution network. Finally, detailed information about consumption enables the building of more reliable decision support models, which are crucial for the adequate management of existing infrastructures and planning of new ones. The possibility of extending the lifespan of the infrastructures through a better maintenance, particularly in a context in which water consumption tends to decrease, enables a reduction of the capex in infrastructures. 6. Improvement of the system's reliability and resilience. In situations of water shortages, SM can create conditions for prioritizing water consumption according to contingency plans, for example, assigning priority to consumption in hospitals. Additionally, through the reduction of water losses, by promoting the efficient use of water and the reduction of consumption in peak hours, better water demand management, SM also contributes to increase the network efficiency, improving the system's reliability and resilience. 7. Value-added services. The water companies can also utilize the data to provide a detailed information to the customers about the water consumed by them and can also inform them, using alarm technique, of any leakages that has been taken place in their respective buildings. In addition, the insurance companies frequently provides the solutions to contribute to the material compensations in case something unpredicted occurs that damages the household of the insurance holder or his neighbors. The timely communication of the existence of leaks in the customer residential plumbing can diminish the potential damages, dropping the risk related to the house insurance premium paid by the insurance holder. 3.4 Challenges of drinking water. Emergency response. Many researchers have summarized the minimum standards for drinking water quality for emergency response specified by the STIA Handbook of Humanitarian Charter and minimum standards in disaster response, chlorine Residual, 0.5 mg per liter, turbidity, 5 NTU, no fecal coliform, FC, per 100 ml. And no undesirable effect on health due to short-term intake. However, treating water in an emergency is very difficult due to numerous constraints. Water quality problems. There are several ways that can contaminate the surface water that are natural. Disasters that results in increasing the microbial population in the surface water. On the other hand, the water quality can be destroyed even by salinization or even due to the release of hazardous pollutants into the surface water. Due to 2011 Japanese earthquake, the water bodies were contaminated with high amount of radionuclides. Debris contamination took place and water turbidity was also increased to 10,000 NTU. The above example shows the results that are obtained due to the occurrence of a disaster. Due to overloading of the heavily contaminated water into the treatment system, probability of failure increases. And moreover, due to this, substantial removal of these hazardous materials is essential in order to make it fit for drinking without causing any adverse effect on the health and well-being of the public. This adds to the complexity of the treatment system. In addition, due to the increase in rainfall, these hazardous materials, heavy metals, could get mixed with the surface water, resulting in resolubilization and a sudden increase of dissolved organic carbon into the surface water. The heavy metal resolubilization accelerates the phenomenon of membrane fouling when treated in the water treatment plant. Moreover, there is a possibility of formation of the as well as taste-problanes will occur when these are treated using chlorine as a disinfectant. Moreover, due to the introduction of irregular chemicals into the water treatment plant, the process unit operation may fail sometimes to execute higher removal efficiencies. This is especially true for WTs such as coagulation, flocculation, adsorption, and high-pressure membrane filtration. Other problems are water quality inconsistency and the lack of on-site toolkits for quick pollutant screening in emergencies. Limited access to infrastructure and resources. Limited access to the infrastructure and resources further complicates the process of providing water. One probable consequence of a disaster is power breakdown that prevents using energy-dependent water treatment system. Water treatment systems that do not need energy from power grid or can use renewable energy harnessed on-site are an option. Alternatively, a mobile electric generator can be used. Disasters such as earthquakes will result in infrastructure damage and limit access to the impacted regions. Hence, other means of access such as air transportation are required, in which case the size and weight of the water treatment, WT, can be limited. These considerations also limit manually transported devices. In addition, during emergencies, trained operators for the water treatment, WT, might not be available, that can result in improper process control and failure. Unhygienic conditions in relief camps might result in post-contamination of treated water. Most Ws other than chlorination provide only interim disinfection due to the absence of residual disinfectant. Hence, it is better to treat water at the point of consumption for WTs that cannot provide secondary disinfection. 3.5 Summary. Monitoring and auditing plays an important role in all the water systems. Water monitoring helps in seeking information about various water quality parameters, and auditing deals with the information about the water supplies and demands. SCADA is one of the systems that can online look over the activities taking place in the water systems. Right from water intake structures to the distribution mains till the consumers, and the SCADA helps in monitoring and data recording as per the requirements. The uses of water smart metering has also been discussed in detail in the above sections, since the conventional meter reading necessitates particular department to visit regularly to the location of the meter and record its reading. Therefore, these all emerging technologies have simplified the work along with rendering high efficiency than the conventional methods. Thank you.